here's my hometown. Anyways, let's do physics. So here's an example of a constant acceleration problem where you have an object slowing down, or in this case, a car. So if you like, pause the video, copy the problem down and the different parts. So I will show you how to attack all these different parts, okay? As fast as I can. All right, so here we have a car initially moving at a speed of 32 meters per second and it slows down at a constant rate of 4 meters per second square. And it said that if the car's initial position, aka its xi, is negative 14, as depicted below, determine the following. So here's the diagram for you, okay? So here's a car. I do want to encourage you to read the wording a little carefully as you practice this problem. Here says the car is initially moving at a speed of 32. Because the word speed is used, it doesn't really indicate whether the object is moving left or right. And so if I see speed, really you're given a choice. You can draw the diagram moving leftward or rightward. In this case, I have my little image here moving to the right. Why? Because I think it's just easier to do, okay? So when you're given the choice, I encourage you to just make the initial velocity moving to the right. So if you use speed, you have the option, pick the better option. Keep things positive. But here it says slows down at a constant rate of 4 meters per second square. And this way, if you're not careful, you're gonna get play in terms of what's given to you versus what should be used in your calculation. So why is it slows down at a constant rate of 4 meters per second square? It's important for you to understand that acceleration is a vector. So therefore, you have to make sure you use the right directions, okay? So watch my diagram, and so you have to understand the diagram before you watch the rest of the work. Otherwise, if you practice, you'll get play. So the word speed implies left or right. I have chosen to use the car going right. So here's my velocity vector. I'll draw my velocity vector at a rate of 32 meters per second moving forward. You have a choice, make the better choice, okay? Here it says slows down at a constant rate of 4 meters per second square. So while the wording just gives you the magnitude, it's important for you to recognize physically what's going on with the scenario. Here, it slows down would imply that the acceleration vector, based on my choice for velocity, needs to point in the opposite direction. So if I want to have the car moving rightward at a rate of 32 meters per second, in this case, if it slows down, my acceleration vector must be pointing in the opposite direction. Okay, so the blue vector here represents acceleration, and it must point left based on my choice for v. Now, had you drawn the velocity vector going to the left, then the acceleration would be pointing to the right. Slows down suggests that these vectors oppose each other. Okay, so v and a have to be opposite. So if v is positive, a has to be negative. But you notice here, I purposely put 4 meters per second squared because that's what the statement says. However, because acceleration is a vector, you must use a negative sign. Otherwise, your calculation is going to come out kind of whack, okay? So let's go ahead and knock these problems out, or parts out. Part A asks us to find the instantaneous velocity at 3 seconds. This is pretty light work. I think the easiest way to do it is using the velocity function, which is a times t plus vi. The acceleration here, you notice here, this is key. While the statement tells you it is a constant rate of 4 meters per second square, if you draw a picture like I did, based on my choice, the acceleration vector is pointing left. Because it's pointing left, you have to put in a negative sign. Because if you don't put a negative sign, it's going to mess with your answers, okay? So A is negative because in my diagram, it is pointing left. So you need to learn to introduce these negative signs when appropriate. Okay, so here it is appropriate. So negative 4 meters per second square, change in time would be 3, because that's what it asked me. So I want to start at 0 second and just go to 3 seconds. So the difference would be 3 seconds. But if I start at 0 second, the statement said that the car was initially moving at a rate of 32 meters per second. And I've chosen right to be positive. That's my initial velocity. So here, my initial velocity would just be 32. So if I just simplify my work here, negative 4 times 3 is negative 12 meters per second. And then I'm going to add the 32, which I've just carried down. So really, at the end of the day, you can just simplify this stuff. Negative 12 plus a positive 32 will leave you a value of 20 meters per second. So the magnitude, or the speed, is 20 meters per second. But because it asks for instantaneous velocity based on my choice of reference, which is moving to the right and coming to a slowdown, I have indicated here, or included the direction. Velocity is a vector, so therefore you should include a direction. So it'll be 20 meters per second, comma, ease, or rightward, or you can just simply use the plus sign in front of the 20, okay? All right, so let's do this an alternative way. The second part, which I don't recommend, but this is just to show you based on how good you are with these kinematics equation, you either pick the quickest approach or you pick the long way. Had you chosen, let's say, to start with this average velocity function and solve for VF, because it has a VF in it, it's okay. In order to get VF by itself, multiply both sides by 2, which I've done here, but at the same time, here is a positive VI. So to get rid of the VI, I will minus it from both sides, which looks like this in my second line. So I've done a couple algebra steps in one. So do that for yourself if you need to. Okay, and now we just plug and chug. 2, my displacement here, I don't know. My time, I do know, which is 3 seconds. And then my initial velocity, again, I'm starting at 0 second, would indicate that my velocity is 32 meters per second. So you notice if you take this approach, you're kind of stuck here, right, where you don't know what the displacement is for the first 3 seconds. But that's easy to find. If your kinematics equation is solid, you should be able to bust out this function. Displacement is equal to VI times t plus 1/2 AT squared. Where here VI is 32, t is 3. The acceleration, again, must be a -4. So you put in a +4, you're going to get play. And then the time here is 3, and don't forget the square. If you simplify this in your calculator, you should get an answer of 78. Okay. So the 78 is your displacement, so therefore you can substitute in for delta x in the previous statement that you don't know. So from here, it would just be 2 times 78 divided by 3 minus 32. So if you simplify all that work down in your calculator, you should get the same magnitude, which is 20 meters per second. And again, because it asked for instantaneous velocity and it did not use the word magnitude, I'm going to include the direction in this case. It will be 20 meters per second, ease, just to be consistent. All right, now let's move on to B and C. Okay, part B asks us to find the time required to bring the car to a complete stop. This one's pretty straightforward. The average acceleration function is final velocity minus initial velocity over a change in time. Here it asks us to find delta t, so I would multiply both sides by delta t, at the same time divide both sides by a, or I would just tell you move the delta t in the numerator to the top, move the a down into the denominator. It's a little switch swap. So that's what it looks like. Okay, so I really have to swap out delta t for a and then bring a down. You can do this because really you're just multiplying and dividing at the same time. All right. VF here is 0. Now why is it 0? Because it says to bring the car to a complete stop, suggesting that my final velocity is 0. Here's the minus sign, which I've carried down, and the initial velocity in this case, again, based on my choice, it is a positive 32. And then the acceleration is a -4 meters per second square, and then the units will cancel out. So once everything is in the proper units, things will cancel out naturally. So here I'm left with 8 seconds. 32 divided by 4 would be 8 seconds. So that's how much time is going to bring the car to a complete stop. Okay. All right. So here's part C. Part C asks us to find the distance required to bring the car to a stop. So how far did this car really travel once it comes to a stop? Well, right away, I can use this particular function because it's time independent. And why would I want to do this? Because I know my final velocity is 0. So as you practice, hopefully get onto the kinematics equation or function that allows you to just complete your task as quickly as possible, okay? I've chosen this, why? Because VF is 0, so I can cross that out. I know my VI, I know my A, so really all I have to do is solve for delta x by manipulating this function. So to get delta x by itself, I simply divide both sides by 2a, which is what on the left side here, the equal sign. So here I have negative VI squared divided by 2a. I know my VI is 32, and I know my A is -4. So I'm just going to plug things in just to show you. The negative sign in front of the function I've carried down, and then 32 square, and then here's 2, acceleration is -4. So it'd be 32 square divided by 8, because 2 times 4 is 8, or -8 if you want. But the negative signs here will cancel out, okay? So you'll get the same value, you get a value of 128 meters. Now because it asks for distance, distance is a scalar quantity. So here, even though I solve for the displacement, because I know during this time, the car has only gone one way. It's moving to the right. Even though I solve for displacement, the magnitude of the displacement, the 128 meters, is the distance. So I really don't need to include direction. I know it's moving rightward, but I don't need the direction because the question asks for distance with just a scalar. So I'll just leave my answer as 128 meters, okay? The alternative way to do it, just in case you need to do extra practice, here's my displacement function that I previously used in the previous slide. Delta x is equal to VIT plus 1/2 AT squared. Well, I know my VI is 32, which again is stated in the problem, and I've chosen to be positive. How much time has gone by? 8 seconds. How do I know it's 8 seconds? Well, we just calculated 8 seconds in part B. It says how much time was required to bring the car to a stop. Well, we just calculated in part B here in red where I'm circling, and we found that it would take the car a total of 8 seconds to come to a complete stop. Okay, so this is why delta t is 8 seconds. It's 8 seconds because I'm trying to find where it stops. And then from that, really, everything else you know, a is -4. Again, the t is 8 seconds. So if you simplify this, you get 256 plus, here I've chosen to use parentheses because a half times a negative times a positive gives you a negative value, and that plus sign is part of the function. You can do this algebra however you want. You can simply just take 256 minus 128 because that's what it looks like, or you can add a negative. I just did this just to show you what I did in calculator term, okay? All right, so if you simplify this statement, you should get 128 meters. Again, no need to include direction because it asks for distance. All right, so here's part D. Part D asks you to find the car's position at 5 seconds. So where is this car located along the number line at the moment 5 seconds pass? Okay, so I like to point out that, this is pretty easy to do. Use the displacement function. Now, why? Because it asks for x of t, and x of t is really x final, which is hidden in delta x. Okay, so delta x is the condensed version, the combined version of xf minus xi. So here you can just use this function to find delta x. You know VI is 32. You know change in time is 5 seconds. Again, I've chosen to start my problem at 0 seconds because I think that's just easy to do. The initial conditions given, I know my initial velocity, so why not? Here's my acceleration. It's important that you plug in a -4. Even though my diagram has a +4, the wording has a +4, you need to know that the vector itself, the arrow is pointing left, so you need to put in a negative sign even if it's not provided for you. So don't just look at the value, understand what's the vector and what's the scalar. And here I plug in 5 seconds, square that, and if you simplify this on your calculator, you should get 160 meters plus -50. Okay, so 160 plus -50 would just give you a positive 110 meter. So you're not done yet though, right? The 110 meters just represents the magnitude of your displacement, but you weren't asked to find displacement. You were asked to find the final position. So a rookie mistake is that kids sometimes just stop here, and I'm like, no, it didn't ask you for the overall change. It asked you where you're at 5 seconds. So therefore, you need to take it a step further. So delta x then can be broken up to xf minus xi. Well, you're trying to find xf, so therefore you need to get rid of xi. Okay, a little quick algebra manipulation. Okay, but it's important here to understand at the very top where it just came up, the red box. It says here that your initial position at time equal to 0 is at -14 meters. So don't just assume that xi is 0. Make sure you guys read, make sure you guys look at different schematics if this is provided for you. In this case, I like to point out that xi is not 0. In the statement itself, it says the initial position, the car is located at a position of -14, which is to the left of 0. So make sure you plug in things carefully. So here, delta x is 110 meters, which we just calculated. Xf is the variable we're trying to find because this is the xt, which is the same as xf, minus, which is the function itself, but xi in this case is a -14. So I like to use parentheses to when I do my substitution so that I don't have any algebra error. A negative times a negative makes a positive, so that's going to look like this. Okay, so therefore to find xf now, I would just have to subtract both sides by 14. So 110 minus 14 will give you a value of 96. Now in my answer, it'll be 96 comma east because position is a vector. So while it started at -14, 5 seconds later, it has gone past 0 and it actually got to the 96 meter mark on a number line. Okay, so that's that. Now, If you wanted to, you can also just do this, but you can introduce xf and xi from the very get-go. Delta x, again, can be broken up to xf minus xi if you wanted to introduce that right away rather than doing it in quote-unquote 2 steps. Well, if we're trying to find xf, we need to get rid of this negative xi. Well, to get rid of it, just do the opposite operation. So if there's negative xi, we add it to the other side. Okay, so therefore that would give us xf, or isolate for xf, and that'll be vit plus 1/2 at squared, which is the same. And now on the right side we have a plus xi, but we know everything already. We know vi is 32, the change in time for this problem is 5 seconds, the acceleration is -4, the change in time again is 5 seconds, and I want to add, but here I'm adding a -14 because the position itself is located at -14. So make sure you're really good about substitution and that you have good habits. Otherwise, your answer might be off, and that could screw with you on a quiz, or an assessment. All right. So here, if you simplify stuff, 32 times 5 is 160. 1/2 times -4 times 5 square will give you -50. And then the -14 is just your initial position. So really you have 160 minus 50 minus 14. And if you do that properly on your calculator, you should also get a magnitude of 96 meters, which represents, where the position is. And then it's got to be east because the car is moving to the right. So your final position is 96 meters on the number line. Okay. Let's do part E. Part E asks you to find the average velocity between 1 and 4 seconds. This one's pretty straightforward. To find average velocity, you have a couple of different options. Here, your first option is delta x over delta t. This function works all the time, regardless of what your a is, whether it's constant or not. So average velocity is just simply your change in position over your change in time. And then so we can just kind of plug and chuck here. You know that the change in time is 3 because the difference between 1 and 4 seconds is 3 seconds. 4 minus 1 is 3. However, you don't know what delta x is. You don't know what delta x is, but that's okay. Go find it. Use your displacement function. Find delta x. Here, though, I like to caution you. vit plus 1/2 at squared. But it's important that you understand where the problem starts. This particular part E starts at 1 second. So at 1 second, the car is actually at a speed of 28. It initially moves at a rate of 32, but it's slowing down by 4 every second. So I'm going to take this 32. 1 second later, I'm going to minus 4. Why minus in this case? Because it's slowing down. So therefore, the next speed would be 28 meters per second. Okay. So because the problem starts at 1 second, my initial velocity is actually going to be 28 meters per second. So if you didn't understand that, you might want to pause and go back and kind of understand that part. Do not plug in VI's 32. VI is only 32 at times equal to 0. But this particular part starts at 1 second and you're slowing down. But the acceleration is 4. So 32 minus 4 will give you a speed of 28. So here's my initial velocity. I don't need to include the direction here for my calculation purposes. Okay, so it'll be 28. The change in time again is 3 seconds because 4 seconds minus 1 second is 3 plus 1/2. The acceleration is given in the diagram. Time is again 3 seconds, and don't forget the square. So if you simplify this stuff, you should get a displacement of 66 meters, okay, to the right during that time interval. But here I just have 66 meters. But really, displacement is a vector, so have good habits, comma right, east, whatever it is you want. But I want to carry this function down. I want to substitute that in. So therefore, the average velocity is simply 66 meters divided by 3 seconds, and which is 22. And then the unit would be meters per second. And notice here, I've included the direction because the question asks for average velocity. And I do not see the word magnitude anywhere, so I do need to provide a value plus the direction in my choice of reference, which is making the diagram go to the right, okay? So if you happen to draw the diagram going left and slowing down, then you would say west rather than east. That's the U choice. All right, so here is the second approach to do it. Average velocity can also be calculated by simply taking the final velocity plus the initial divided by 2, okay? And you can only do this when acceleration is constant, and it is for this particular problem. So, easy work. All you have to do is use the final velocity function a couple of times. A times c plus vi. So here our 2 times are 1 and 4. So find the velocity at each of those time slot and then just plug them in. So here I did 1 second first. The acceleration is -4. The change in time here is 1. I've started from 0 second to 1 second. Okay, so again, I started the problem initially at 0 second, and at 0 second to 1 second is a difference of 1 second. But if I start a problem at 0 second, my initial velocity must be consistent, and that is, it is already moving at a speed of 32 meters per second. So if I do this and I simplify, it'd be -4 times 1, which is -4, and then -4 plus 32 is simply a positive 38 meters per second. So that's at 1 second, but I need to do the same function again. Now I need to do it for 4 seconds. So really, I need to find two velocities at those times. So this function allows me to find this velocity. Here I've chosen 4 seconds. The acceleration stays the same, which is -4. I've chosen to start from 0 to 4 seconds again. So therefore my change in time is 4. But if I start my problem at 0 seconds, my initial velocity is 32. So -4 times 4, which is 16, and then, or -16, and then -16 plus 32 is a positive 16. Now, therefore, you can just carry this function down. You just found two values. You found VF and you found VI at 1 second and 4 seconds. So your two values are 28 and 16. So all you have to do is you can just add. In this case, you can write VI plus VF or VF plus VI. I don't really care. It's the same. You're just adding. So the order of the variables can be swapped, okay? And you need to divide that by 2. So here, my final velocity is at 4 seconds, which I calculated to be 16. And then my initial velocity at 1 second, which is 28. And then 16 plus 28 is 44. And then 44 divided by 2, which is 22. Here is meters per second. Again, it says average velocity, so I'll include the direction east just to be proper. All right, let's do part F. Part F is a little more tricky, and so I think you need to emphasize or focus here on part F. And I want to emphasize a couple of things, okay? Here it asks for average speed between 0 to 11 seconds. And this is usually where kids might struggle in terms of finding this particular quantity. You need to recognize that the car, based on my velocities here, stops at 8 seconds, okay? In part A and B, we kind of use the calculations where it asks how much time would it take for the car to stop, and we find that time to be 8 seconds, okay? But here, I notice that it asked me from 6 to 11 seconds. Well, the car stops at 8 seconds, and then the acceleration is negative. So in this particular scenario, it would suggest that the car or particle or object actually moves to the right, slows down, and actually gets pushed in the opposite direction or turns around. How do I know that? Because the car stops at 8 seconds. And if the object experiences a uniform acceleration in negative, it actually stops at 8 seconds and then turns around and moves leftward. Okay, so that's important. So I want to start with the average speed function. The average speed function is distance over time, but I need to find what that total distance is. When an object turns around, you have to recognize that you cannot just find displacement. You have to use the displacement function a couple of times in order to find the total distance. So hopefully my work makes sense here. Okay. 1, I need to find the distance from 6 to 8 seconds. Now, why start at 6? Because the problem starts at 6. Why would I stop at 8 seconds first? The car took 8 seconds to come to a complete stop. So it's moving to the right, and all of a sudden at 8 seconds it stops. So I need to find what the distance is between 6 to 8 seconds, okay? So I can use the displacement function. Here I have VI delta t plus 1/2 AT squared, but I'm going to plug in VI as 8. I'm plugging VI as 8 because this particular part starts at 6 seconds. And if you look at the top of the screen here where everything's in green, I've listed the velocities at each of the seconds, okay? So it starts off at 32 and it slows down by 4 each second. That's what acceleration tells you. It tells you the change in your velocity. So at 6 seconds, which where I'm going, at 6 seconds, my velocity is 8 meters per second east again, but I'm going to leave out the sign in terms of my calculation. So VI here is 8 seconds for that reason. The problem starts at 6 seconds. Now, delta t, what's delta t? Delta t is actually only 2 seconds because the difference between 8 to 6 is 2 seconds. And then the rest of the work here is kind of, just the same. Plug in A, plug in t, and t being 2 seconds. Not 6, not 11, not 8. Why? Because I need to go from 6 to 8 because that's where it comes to a complete stop. So if you simplify this on your calculator, Okay, you should get a value of 8 meters. So how far did the car travel between 6 to 8 seconds? A distance of 8. So why I use the displacement function, I note that the car is moving to the right between 6 to 8 seconds. So therefore, really, I can use my displacement function, and finding the magnitude will give me the actual distance, okay? I don't need the include direction because distance is a scalar. So I've done one part. But this particular part here went from 6 to 11. So I'm not done yet. I just went from 6 to 8. Now I need to go from 8 to 11, okay? But the car's going to turn around, right? Let's say you put on reverse or it comes to a stop and then you put on reverse and hit the gas. It's moving left now. So I need to go from 8 to 11. So I can use the same function, but now my bounds are different. The values I'm going to be using are different. I need to plug in VI as 0 because if I start at 8 seconds, my velocity is now 0. So the final velocity now becomes your initial velocity. So at 8 seconds, the car came to a complete stop, which implied now the initial velocity must be 0. The delta time would be 3 seconds because the difference between 8 to 11 is 3 seconds. And then the acceleration stays constant throughout the whole thing. And then t here is 3 seconds, and we got to square that. And if you do this, you can cross out the first term because it's kind of stupid. Again, I'm not just writing the 0 for you to understand where the 0 comes from. I start the problem at 8 seconds now, therefore my initial velocity must be 0 because it did come to a stop. And now it's going to start going backward. So if you do that, it tells you that the car is actually going to travel a displacement of negative 18 to the left now. But I just need the distance, okay? I just need the distance. I know it's going left, but I don't really care for the direction. I just need how far it went because it asks for average speed. So really here, the 8 and the 18 gets added together, okay? So it's important for you to understand. Here, I purposely did not circle the negative sign. The negative sign is the direction for your displacement, but I don't need displacement. I just need the distance. So in this diagram, I visualized the car moving to the right 8 meters, and then it went back to the left 18 meters, so a total distance of 26. Okay, so do not add a negative. Distance is a scalar. So 8 plus 18 is 26, and then 26 divided by 5 is simply 5.2 meters per second. Okay, no directions needed because the average speed is a scalar. All right, last part, it says to find the ratio between the change in velocity between 2 to 6, which is equal to, some unknown ratio here, some unknown coefficient of the change in velocity between 6 to 8 seconds. So I'll show you how to do this properly, but hopefully as you practice, the coefficient becomes a little easier to find. All right, I'm going to start with my average acceleration equation, which is delta v over delta t. I want to isolate for delta v. I will keep that condensed because the question is asking me to compare delta v. It didn't say vf, it didn't say vi, it said delta v. So I will keep this as delta v. So I need to find delta v between 2 to 6 seconds, and then delta v between 6 to 8 seconds, and then from there, I can find this missing coefficient, or aka blank, super fast. So I want to apply this function twice. Okay, here I am going to go ahead and apply a is -4, and then the first time interval is 4 seconds. You notice here I want to keep delta v as delta v. I don't need to break it up into vf minus vi because that's not the question it's looking for. It's just looking for the change in velocity during this time interval. So here 2 to 6 seconds is a difference of 4 seconds. So the change in velocity on the left side is -16 meters per second. I can use the same strategy to find the change in velocity between 6 to 8 seconds. Okay, so here a is -4 still. The change in time, however, is only 2 seconds because from 6 to 8 seconds is a difference of 2 seconds. And then -4 times 2 is just -8. So here I have my two values and I can just plug it in. According to the statement, delta v from 2 to 6 is on the left side. I just found that to be -16 equal blank. And I just found the change in velocity between 6 to 8 seconds is a -8. And I would just encourage you to just use the symbol heart, again, or whatever symbol you want, and put that in the place of blank, and then solve for heart. So in this case, to get heart by itself, you have to divide both sides by -8. You notice here, this is a little deceiving. You might think this is -8, but if you're listening, this is the multiply, okay? So therefore, to get heart by itself, you would divide both sides by -8. -16 divided by -8 would simply leave you with just a coefficient of 2. And this coefficient has no unit because meters per second on the left side and then meters per second on the right side will naturally cancel. So really this coefficient just tells you that it's a 2. 2 times negative 8 is negative 16. So it makes it a true statement. Okay? All right. I hope that helps. Stay nerdy and don't be whack.